In this video, we're going to take a look at one-sided limits. We're going to be looking at what's the limit as x approaches c from one side as opposed to approaching it from both sides. We're going to use this notation. This first one has x approaching c with the positive, sort of like an exponent or superscript up there. This is going to be from the right, a limit from the right on the plus side. Right? So on a number line, the bigger number is to the right. We're going to be actually approaching from the right, heading back towards the left. When you see the negative sign up here, you're going to be approaching C from the left. Okay, so let's look at this first column right here. The limit as x approaches 2, right? As x approaches 2 from the left, right, we're starting to the left of x equals 2 and getting closer to it. We're going to slide up the curve. The closer the x coordinates get to 2, the closer the y coordinates get to 4. Okay? As we approach 2 from the right, we're going to start to the right of 2 and head back, so maybe at 3 and then work our way back. And then we're going to try to follow on this curve here, right, heading back down to also 4. Right? And we've probably done enough with limits at this point to understand that the two-sided limit did exist here. We have a point of discontinuity, right? Because the function doesn't exist at x equals 2, but the limit does exist. And because the two one-sided limits agree, right, we can certainly say that the two-sided limit is the same as the two one-sided limits. Right? But when we move over to the other point of discontinuity and look at x approaching 5, as I approach at 5 from the left, I'm up here on this piece of the curve, right? And I'm going to be approaching the y value of 5. Right? So if x is something like 4, 4.5, 4.9, 4.99, the y values are going to get closer and closer to 5, even if they never actually get there. As I approach 5 from the right, I start to the right of 5 and start heading back. Now my y values are getting closer and closer to 3. Right? Now, the two-sided limit, this is always a limit that we said didn't exist, right? Because you can't answer the question of the limit unless you ask what side you're coming from, right? So we still say this limit doesn't exist, but now we can see what's going on here, right? When the two one-sided limits don't agree, then the limit doesn't exist. And when the two one-sided limits do agree, right, then that two-sided limit exists. So now we'll be able to look at one-sided limits from a graph and determine them, even in cases where the two-sided limit doesn't exist. But we also have to figure out how to handle this when we don't have a visual and we have an algebraic representation of a function. So a couple things here we're going to talk about. First of all, that we're going to say that a limit exists, and the limit of f of x as x approaches c is going to be L if and only if the left-sided limit and the right-sided limit both agree. Right? So when we have a piecewise defined function like g of x down here, and our goal is to find the limit as x approaches 4 of g of x, right, we don't have a picture to look at, and you might have enough ability to draw a picture, but it's a lot of extra work that we really don't need. We have a line segment and a line, I guess, a ray and a part of a parabola, and we have to figure out where they come together. Now, x plus 3 is continuous. X squared minus 7 is continuous. The real question is, as x approaches 4, where we put our open and closed circles, right, what's going to be happening there? So rather than drawing a graph and trying to answer this visually, we can make this a limit question, right? The limit as x approaches 4, so I'm having a little trouble with the pen, from the right of g of x, right? If you're approaching 4 from the right, that means you are bigger than 4, right? Which means you're on this rule, right? So as x approaches 4, you're something like 4.1 or 4.2, 4.01, then you're going to be following the rule x plus 3, which is going to be 7, right, in this case. Now, if we're approaching 4 from the left, right, that means we're less than 4, right? We're to the left of 4. So this limit is going to be x squared minus 7, or 16 minus 7, which is 9, right? So because the one-sided limits don't agree, we can say that this limit doesn't exist, right? So most functions that we've studied, the left and right-sided limits, are going to be the same as the actual function value, because most of the functions we've studied are continuous everywhere. But piecewise defined functions give us a nice example of an algebraic function where the left side and right-sided limits don't agree. A function that gets used quite a bit in computer science, but also has some applications in math, is what's called the greatest integer function. Okay. It can also be considered the floor function. And what it does is it gives you the greatest integer that is less than u, less than or equal to u. So, for example, when you look at this first piece over here, right, when the x coordinates are 0, 0.1, 0.2, 0.3, 0.5, all the way up to 0.99999, we drop down to 0, right? But the minute x becomes 1, we hop up to 1. And then for 1.1, 1.2, 1.5, all the way to 1.999, we stay at 1. And as soon as we hit 2, we jump up to 2. This is sometimes, these types of functions are called step functions. You can see that the line segments here look like steps. And just as some example, 3.5, right? The greatest integer would be 3, 3, 3, 3. It doesn't matter if any 3 point anything, right, is going to drop down to 3. That's why it's called the floor, because it drops down. You got to be a little bit careful with negative numbers, right? Negative 3.5, it might be tempting to say that the floor is negative 3, but negative 3 is not actually less than negative 3.5. So with negatives, right, in order to get less than, you have to go down to the next negative integer. Right? These would all be negative 4. Right? So, with this picture, it's easy to answer these two limit questions. But if we didn't have them, right, in front of us, the picture, we could think about something just to the left of 0, right, which would be something like maybe negative 0.1. This is a little bit tough writing here. 0.1. And that would have to drop you down to negative 1. But if you were just to the right of 0 at 0.1, you would be at 0, right? Which we could see here and here from the picture. But if you didn't have the picture, you could use the greatest integer function. So this is another sort of common example. It's not something that you really have to worry about usually on tests and quizzes, the greatest integer function, but it does create a nice example of a piecewise defined function that does have limits that are going to be different from the left and the right, in this case at every integer.